Greetings everyone and welcome back to the bench. Time to move ahead on the Discrete audio amplifier project. Today I want to talk about loop stability. In other words, how to make this amplifier be stable when we apply negative feedback. See, negative feedback is a loop, and if the phase of the signal coming back is in phase with the input signal, then the amplifier can oscillate. So we need to do what's known as compensation to correct for that. And since we're dealing with negative feedback, I think it would be good to understand what's going on there. So I'll make a little feedback amplifier circuit and demonstrate how gain and the correction and everything works. So what I have here is a simple amplifier diagram which we can use to explore negative feedback and how it works. Of course, this triangle symbol is the operational amplifier, and our audio amplifier pretty much is a power op amp. So we can use this in our demonstration here. So the op amp will have a non-inverting input represented with the positive symbol. The negative symbol represents the inverting input. And as this is configured, it's a non-inverting amplifier because the input signal, which is fed into the non-inverting input, has the same phase relationship with the output signal. If we fed it into the inverting input, it would be 100 degrees out of phase at the output. Now I'm using what's called an ideal amplifier. The reason I am doing this because it makes it very easy to understand. If I threw in all the variables to what a real world amplifier is, it would confuse somebody that's trying to learn this stuff. It'd become a lot more complicated. And the ideal amplifier will get us 98-99% there anyway, so it makes sense to use that. But I will throw a few comments in at the end to explain how the real world amplifier would differ. So what are some of the attributes of an ideal amplifier? Well, it has infinite input impedance, zero output impedance, and infinite open loop gain. But don't worry about open loop gain in this discussion. It doesn't really apply to any of our calculations with the ideal amplifier. Also, the negative feedback loop will make the voltages here equal. In other words, the difference between the voltage on these pins are going to be zero. So with our negative feedback, we take the output and connect a couple resistors in series to ground. The node between the two resistors will be some fraction of the output voltage. So this acts as a voltage divider, as they call it. So a fraction of the output voltage is sent back to the inverting input. Now, if this line was not connected, the amplifier would be operating in open loop condition. And because the gain is very high, even in a real world amplifier, the gain can be like 100,000. So the smallest voltage would slam the output voltage to the rails. In fact, even small offsets in the amplifier would push the output to one of the rails. So in our case as an audio amplifier, that wouldn't be very useful. So we close this loop here by connecting this line to the negative feedback, and that controls the gain of the circuit. And with the non-inverting amplifier, this is what the gain would be. It would be R1 divided by R2 plus 1. So in this case we have 20K resistor over a 1K resistor. So it's 20 plus 1. So in this case the gain is 21. So in other words, if we put 1 volt on the non-inverting input, we'll get 21 volts out. And of course that would be limited by what our supply voltages are. By the way, supply voltages are not shown in this demonstration. They're assumed. You often see gain represented with an A subscript CL, indicating that it's closed loop gain. Okay, it's your favorite time, mathematics. Let's apply some mathematics and see what happens with this circuit. Demonstrate some conditions of this negative feedback. Well, first let's see what's happening here. Well, we put our 1 volt in and we're set up here to get 21 volts out. With 21 volts out flowing through this resistor, let's see how this is stable if it's meeting our conditions that we mentioned earlier. Well, if we have 21 volts and we have a 20K and 1K resistor in series, so the current flowing through here will be 1 milliamp because it's 21 volts divided by 21K. And with this ground being our zero reference, we can calculate the voltage at this node. It's just the current through this resistor, which is 1 milliamp times 1K, 1 volt. So we have 1 volt here and 1 volt here, so that meets our condition that these will have the same voltage on them. Let's say our ideal amplifier has a non-linearity. It's not really ideal anymore. I mean, it still has infinite input impedance, zero output impedance, but it has a non-linearity. In other words, we put in 1 volt, but let's say we're only getting 20 volts out. We can see how the negative feedback is going to correct that condition. So we'll have 20 volts over 21K, and we multiply that by that 1K resistor to get the voltage, and we end up with 0.952. Well, now we have 1 volt here and 0.952 here. Well, the condition is no longer met that these are the same. So that's going to generate an error signal that the amplifier is going to push through its circuit and correct that output. Now, because this is an inverting pin, this will actually be a negative value. So we take 1 volt minus this. So 1 volt minus 0.952 gives us 0.048. So now we'll multiply this by what the gain of the amplifier is supposed to be. So 0.048 times 21. And we get 1. So if we add 1 to 20, we get 21. So negative feedback is correcting that error back up to the correct voltage. Now let's say that the amplifier has a nonlinearity and thus creating a voltage of 22 volts out. It's coming out a little bit more than expected. Well, we run the math the same way again. 22 divided by 21K, again the sum of these two resistors, times the value of this resistor. We end up with 1.048 volts. So we take 1 minus 1.048, we just have negative 0.048. So we multiply that by the gain, and we have negative 1. So 22 plus negative 1 is 21 volts. You can see that it brings the amplifier output voltage back in line. So that is how negative feedback is correcting the errors in this amplifier, or in other words, the nonlinearities. Well, you might say, okay, that's fine and dandy with DC. What about AC? What's going on with that? Well, it's really the same thing. We're just taking any voltage on the AC waveform at any given time and applying it to the circuit. So for example, if we took the voltage at this peak of the waveform, let's say it was 1 volt, you would just use 1 volt here and run the math. If it was negative 1, or for example if it was negative 0.7 volts, if you measured it at this point, you would just apply the math that way. You're just taking a voltage at any given point in time on the AC waveform and applying the same math. One reason I mention that is because I want to give an example of a distorted waveform. Well, this drawing, it's not a great drawing, but it's a waveform that has second harmonic distortion. Quite a bit as it's drawn. But I did that, to make it look really distorted for visual purposes anyway. So in this condition, it's going to have plus 22 volts at this peak, but at the negative peak where the waveform has lower amplitude but it's wider, it only goes up to 20 volts. So you can apply the same math, what we did here, to show how it cleans up this waveform, this distorted waveform. In this example, we're pretending that the amplifier has a nonlinearity inside of it, causing the output to be really distorted and showing how negative feedback cleans it up. Of course, if you put a signal in that's distorted, the amplifier cannot fix that. It's not within this negative feedback loop. It's not inside the loop or closed within the loop, so it cannot fix distortion that's already present in the input signal. Well, hopefully you can see with this ideal circuit how exactly we can calculate the gain, how the negative feedback is going to remove any of the nonlinearities. And essentially the amplifier would add no distortion at all. But in the real world that's not the case. The amplifier has a finite amount of gain. The inputs are going to have impedance. There'll be a little bit of bias currents flowing. The output will have a small amount of impedance as well. Open loop gain is going to diminish with frequency. So, it becomes a lot more complicated. But with a decent amplifier, the gain is still going to be close to 21. It'll be like 20.9, for example. So using the ideal circuit does get us pretty close. But it's very important to understand, what's really going on with the amplifier. If you remember from my other video about why amplifiers operate so fast, why they have a very wide bandwidth, well beyond human hearing, well beyond 100 kilohertz even. Well, this is the Bode plot I made for that video, giving just an example of an amplifier. It has a lot of open loop gain. This is the open loop gain curve. Starts out very high at 100 dB, which is a gain of 100,000. So compared to the gain that we had set, which was 21 in our ideal amp example, that is a heck of a lot of gain. And like I said in that other video, negative feedback needs this headroom, or what's called loop gain, to function. And at some frequency, the loop gain is going to roll off. It's going to diminish quite a bit. And at the maximum audio frequency of 20 kilohertz, you can see that loop gain has diminished considerably. Remember, these are in dB, so this is logarithmic. But we had almost 100,000 loop gain headroom here. If we only have 34 dB of loop gain here, I'll take 34 divided by 20. That equals 1.7, so it's 10 raised to the exponent of 1.7. So now we have only a gain of 50 to work with here. I mean, that is still working room, but it's a lot less than 100,000, isn't it? Technically 100,000 minus 21, but you see the point I'm trying to make. And since negative feedback does not have that working loop gain, it won't be able to correct for nonlinearities like it could when it had a lot more loop gain. So that's very important to understand with the real-world amplifier. Okay, so now I have another graph drawing of loop stability. So on this side we have the gain of the amplifier in decibels, and that corresponds with the blue lines. And I'm showing two amplifiers, the solid blue line amp and the dotted blue line amplifier. And in this region they have the same gain, so they're overlapping. But the dotted blue line amplifier extends out to a much higher frequency. Now, to keep things simple, I'm showing only one phase response line for both amplifiers. In the real world they would be different, but again, just to keep this discussion simple, I'm just using one phase line. And this purple line corresponds with the vertical axis on the right here, showing phase. Now you see I'm showing two scales here. Well, one I'm starting at 0 and the other 180. Some people like to start at 0, but because we're working with an amplifier that has negative feedback, which the negative feedback would be 180 degrees out of phase, I'm starting at 180 degrees. Now, due to the components in this amplifier, it's going to pick up additional phase shift. You know, there's a bunch of transistors and other components, and they'll have parasitics and characteristics that add to phase shift at higher frequencies. And if you remember filters, how you have a resistor and a capacitor acting as a filter, and at some frequency the response rolls off. Well, at the 3 dB down point, or about 71%, is called the pole. So you hear that term poles a lot. So you can think of those components that add the additional phase shift as poles in the circuit. So at higher and higher frequencies, eventually the phase will shift so much that it is now 360 degrees out of phase if you started at 180, or if you start at 0, it would now accumulate 180 degrees. In both cases, it accumulated 180 degrees phase shift. And because negative feedback is no longer at 180 degrees where it started, it would be an oscillator now because it's positive feedback due to that phase shift. I didn't mention it, but of course this is the logarithmic scale of the frequency on the x-axis. So we'll look at the solid blue line amplifier first. You can see that it's nice and flat, then out to around 100 kilohertz it starts rolling off, and it hits unity gain, or 0 dB, at several hundred kilohertz. Now if we draw a vertical line at that point where it crosses the 0 dB unity gain, draw a line up to the phase line here, and you'll come to a point, and then you go horizontally out and see what degrees of phase margin we have. So that's called phase margin. And you can see we have more than 45 degrees, maybe 50 or 55 degrees of phase margin. And that's good because they say you should have at least 45 degrees of phase margin. So this amplifier should be stable. Another thing we can look at is called gain margin. And if you draw a line from where the phase line crosses 180 degrees or 360 down to the gain line of the amplifier, and you can see that we're well below 0 dB. And we'll just say we're like negative 15. You should have at least 6 dB of gain margin, and of course we're fine there. So now we'll look at the phase response of the dotted line amplifier. You can see that it has nice flat response as well, and it goes out to a much higher frequency, but you can probably already see a problem. If we look at the phase here, where it's crossing 360, and we draw a line up to the gain, you can see that it has significant gain where it's accumulated 180 degrees of phase shift. So this amplifier is clearly unstable. It's going to be a problem. So how do we take care of such a problem? In other words, how do we compensate the amplifier so it is stable? Well, what we want to do in the case of the dotted line unstable amplifier, we want to reduce its response so it's back more in line with this amplifier so that it doesn't oscillate anymore. Of course, in real life, affecting that response will also affect the phase response, so you have to keep that in mind. But what we want to do is add some form of compensation. Now I'm going to be somewhat light on the description of phase or feedback compensation. Now this is where you probably want to pick up one of those audio amplifier design books like Bob Cordell's book I reviewed earlier, because it has a whole chapter dedicated to that. But let's take a quick look. So here's the schematic of my amplifier. If you watch the series, you're probably familiar with that. Well, one type of compensation is called lag compensation, where we just add a capacitor to ground on this VAS stage, or voltage amplification stage, where we just add a capacitor to ground. usually has a resistor in series as well. And that'll roll off the high frequency. That'll slow the amplifier down, and it stabilizes the amplifier. But this is not ideal. A more common compensation scheme is called Miller compensation, where we place a capacitor, usually of a few to several hundred picofarads, across the collector to base junction of the VAS amplifying transistor. It can be in other positions as well, but this is most common with these types of amplifiers. And because of its position across the collector and base of the transistor, it has some negative feedback effects. And it does something called pole splitting, where it brings the pole frequency on the input down and increases the pole frequency on the output of the circuit. And that pole splitting effect works very good for frequency compensation. Now I'll give passing mention to more advanced compensation schemes. Those schemes give you a faster roll-off. That way your open loop frequency will stay much higher, longer, but it'll roll off faster so you don't run into phase issues or phase margin issues at higher frequencies. So at 20 kilohertz, negative feedback has more loop gain available to linearize the amplifier. Okay, so that was quite a bit to get through. I know I presented it a little different than what a textbook would, but I thought it would be in a way that would make it easier to understand, and hopefully it was. And as always, I appreciate good, intelligent comments, appreciate the viewership, and we'll move ahead. We'll take a look at trying different Miller capacitor values, see what happens with the amplifier if we run it with no Miller compensation capacitor, see if it's an oscillator, in the next installment of this series. Well, that's it. Thanks for watching.